Hello everyone, welcome to a new video on the LSA encryption algorithm. Today I'm gonna show you a variation of the algorithm which we call the LSAL. So what is the LSAL for and how does it work? Okay, first we have to recall a couple of things of the LSA. Okay, remember that for secret message of n characters, the cipher text that we're going to throw in the open looks like this. We have C1, which is composed of little c1 and sigma 1, and we have C2, which is little c2 and sigma 2, all the way for n characters to Cn, which is equal little cn and sigma n. And remember that these tuples are disjoint. There is no tuple that contain any information at all about another one. And also recall that this tuple does not contain any information on the group that this element is part of. So there is no way to track back to the group, so there is no way to find the group, to hack the message, unless we make a guess. However, we also know that if we make a guess, the LSA does not give a receipt that the message has been successfully hacked. Okay, so how this is possible? It is possible because each single tuple, so each single character of the message, has been produced by running the LSA algorithm from the very beginning. So again, what we needed for each character, we need to start with a number k. Let's call it k1 for this, k2. We need all of them. We need k3, k4, all the way to kn. And we didn't talk much about them, but these are, we call them secret numbers that Alice and Bob share and no one knows. Okay, so the question is, if Alice has to send a 1,000 characters message, a letter, how do we expect Alice and Bob to be ready with thousands of Ks already? I'm going to show you how we can do it after we ran the LSAL. Also, I want to make a quick note. Since we said that there's no way to track back the group, sorry about this, the group UN, this we will call UN1, okay, by this tuple, because we said we can disguise this just by adding one arbitrarily or subtract, or any way to disguise. We can disguise this element in thousands of different ways as long as the two parties agree. So this can be part of an infinite amount of group. This brings the fact that we do not need large groups. We need a fairly large variety of group, I would say. So we need the chance to have many groups, so that the chance to hack one of this is 1 over the number of the groups. So the only limitation for group is that if I am sending the message and I'm using certain characters, then all the characters that I'm using have to be matched with the element of the group in an ambiguous way, meaning that the group must have a number of elements that is equal or bigger than the number of characters that I'm using. But I prepared this group for you to show you this. This is the graph of phi of n versus phi of n. First, how beautiful this graph is one of the most elegant graph that I've seen. Look, this line over here is all prime numbers, and this are all the integers. Anyway, is really something. Anyways, so as you see, when n increases, basically f of n increases, and how we translate it on the for the LSA is this way: as n increases, sorry about this. Okay, as n increases and reaches 1000, okay, then phi of n is above 200. Or when my un is un greater than 1000, then there are more than 200 elements. And if we this means that if we use an n that is greater than 1000, we are guaranteed to have groups with more than 200 elements, which means that I can fit into the group every printable characters of the ASCII. So we believe that if n is an integer that has between 4 and 10 digits, it is more than enough to guarantee the maximum security that the algorithm can provide. Said that, what is the LSAL? LSAL. The LSAL is meant to produce a very large amount of number k's. Okay, remember, from k we derive n, which is in a certain form, which is in the form of a prime number raised to a positive integer, or twice a prime number raised to the positive integer. This ensures that in the group the multiplication of all the elements modulo n is congruent to -1 mod n by Gauss's generalization of Wilson's theorem. So out of n we're going to find our group un. So this ensures also that our encryption is made character by character, the tuple are disjoint, etc., etc., what we just said before. Okay, so again, we need a large amount of, we might need a large amount of k, so we need to find a way to provide Alice and Bob this large amount of integers. So how will we do? It's very simple. Remember, Alice and Bob, Alice chooses an element of the group un that we called in the previous video, in the first explanation, epsilon sub h. Okay, it communicates tuple, as we just said, c equal little c sigma, sends it to Bob. Bob decrypts the message and finds epsilon sub h. At this point, they ran the LSA and they both know epsilon sub h. So what they both do is simply, let me state clearly here that un is equal epsilon sub 1, epsilon sub 2, epsilon sub h. Let's put epsilon sub h plus 1 and 2 all the way to epsilon sub phi of n. Okay, so what Alice and Bob do is simply epsilon sub 1, epsilon sub 2, times epsilon sub 2 times epsilon sub 3 times all the way to epsilon sub h without using modular multiplication. They just perform the straight product of this and call it m. At this point they have, if we chose the right element and if we have a group obviously large enough, we said above 1000 elements, and you pick an element that is somehow in the middle or greater, then you have a large m. Okay? This number, we want this number being large, and what we do, we simply chop this number so that is into little pieces, and these little pieces are going to be our little case. Let me show you an example. It's easier to do it than to explain it. Remember, we already used U54 in a previous video, so let me write U54 down. And 53. All right. So this is our group U54. I'm going to show you this example, which would not produce a very large m, but this is just to show you how it works. And then I have ready another example for you that we're going to use a group that might be used in reality. Okay, so this is our group, and assume that we're sending that we choose the element 25. So we perform 1, right, times 5 times 7 times 11 times 13 times 23 times 25, which is equal to this guy, 9 2 9 5 5 3 6 2 5. Okay, which is our m. Now there are many ways of how to chop the numbers to find k's. Okay, you can just take four digits and chop it here, and then the 4 and chop it here. What I'm going to do is something that is a little more, I don't know, sparkling to do. Assume that we want, for the sake of this explanation, we want keys that are 2 or 3 digits. So we're gonna take our number and go to the digits that are 2 or 3. So we scan our number, and we'll see that we have a 2 over here. So since we have 2 here, my 2 digit, my first 2-digit key is going to be made of the next 2 digits. So this one here. So we call I don't know, K1 equal 95, and then we move on and find this 3. Remember, we want 2 and 3. So my next key will be a 3-digit number, and it's going to be the next 3 numbers. So this guy's K2 is going to be equal 625. With this number we produce 2 keys. So if we had to encrypt 2 characters, the first character we're going to be encrypted using this. So out of K1 equal 95, we're going to find our first useful digit, n, that is greater than 95, and 1 is greater than 95, and is in the form that I said before. And same here, out of K2, that is 625, we're going to find our n2. Okay, now let me show you an example, a more interesting example. Alright, so these are the conditions. Assume that the first k that we still need, okay, the first sequence number, the one that Alice whispered in Bob's ear is 10,000. Okay, so our n is going to be 10,082, because in fact is equal to 2 times 71 square. Okay, then u1082, which I'm not gonna write obviously, because is composed by 400 is 4,970 elements. Okay, then assume that Alice chooses the 500th element. Okay, then I don't know which one is. I'm sorry about it, but is obviously an integer that is coprime with 10,082. She chooses that. She goes through all the encryption process, the LSA normal encryption process, and sends this sends a tuple to Bob. They decrypt, they get the number, and then they multiply. Once Bob knows which one is the 500, that Alice is pointing at the 500th element, then they both will get the product. They will both get the product from the first element to the 500th element, and this is the result. They will get, we call it M. This is our M. It is nice, because this was, for the computer, was really a breeze. Okay, so assume that we want to out of M we want to get only 4-digit keys, so that our groups are going to be in the thousands. Okay, so then what they do is they check all the digit 4. So this is the first one, and the first key is going to be from here to here. So K1 is going to be 2941, and then I'm going to check the second one, which is this one, and this is going to be the second key, K2 equal 16648. Okay, and this is the list of all the 4-digit numbers. So this is M, and this is the list of the 4-digit numbers that we can generate out of M. Now, if we generate at the same time out of this number keys of 4 digits, 5 digits, and 6 digits, we get 5,277 keys. 5,277 keys. This means that Alice and Bob don't have to share any other secret keys than the starting one since they finish this. So they can encrypt 5,277 characters before having to run the initial key. So I don't know, a Diffie-Hellman algorithm. By the way, sometimes when I say I don't want to mention key exchange algorithms, because I know that they're they're humongous numbers, and people think when I start saying that out of k we want n such that n is greater than k, if people think that k is the Diffie-Hellman and then is impossible for a computer, it's almost impossible even for a computer to get an n bigger than a Diffie-Hellman and that is in a certain form. What I mean is, I don't know, it's up to the user, but in my opinion, run the Diffie-Hellman and get the first 10 digits, and out of that, call that number k and find n, and then out of that n, you find this m and all the other little keys. And this is it. So thank you very much for watching the video. Thank you for your patience. I know it's not easy to follow. Unfortunately, it's not very easy to explain, as instead it's easy to even to run and to use it. So thank you again. I'll see you in the next video.